All right. Hello. So now we're going to go over some ways we can use depth first search to explore the graph and learn about some properties of it. So let's first talk about connectivity in undirected graphs. An undirected graph is connected if there's a path between any two vertices. So first, just recall what a path is. A path in a graph is a sequence of vertices such that between each successive vertex in the sequence, there's an edge in the graph, right? So between V and 1, the V1, V2 is an edge, V2, V3 is an edge, and so on. Now, a connected component of an undirected graph is a subgraph of G such that the subgraph is connected and no vertex in the subgraph is connected to a vertex outside of the subgraph. So a subgraph is just a graph whose vertex and edge sets are a subset of G. So let me just give you an example, and I think it will make it a bit clearer. So let's say I have some graph that looks like this. And it has edges. Maybe it has another vertex here that's just isolated. So the full graph here has 1, 2, 3, 4, 5, 6, 7, 8 vertices and this set of edges. A subgraph is, well, like this would be one subgraph here. This is another subgraph, and this is another. I believe Andy Reid even let him do it. So each of these are connected components of the graph. Three connected components. And you can see each is itself a graph. And so we call those a subgraph, right? This is a special graph with one vertex and no edges, and so on. So when we're running DFS on a graph, we can count the number of connected components in that graph. And we just have to make a small modification to depth first search. So what we do is when explore is called at a vertex V, it identifies the connected component containing that vertex. So each time our DFS algorithm calls explore, we found a new connected component. So let me just go back to the lecture notes from our last lecture and look at DFS, right? Each time in line 5 here, we call explore on a new vertex. That's a new connected component. Explore itself will then call recursively explore, but that's finding everything in that connected component. Then it finishes, it found that entire connected component, and we come back out, we find another vertex in this for loop that hasn't been visited, and we find a new connected component. So all we have to do is have a counter that counts how many times does line 5 get executed. And so to count connected components, all we do is we initialize a counter. It's called CC equal to 0 prior to calling DFS. And then we increment it. So add the line. Connected component count equals connected component count plus 1. Between lines 4, and 5 of DFS. Right, and that will, so right here inside this if statement, we just increment it because we found a new connected component. And that will then count connected components in the graph. Okay, that's something. There's something kind of, I think, more interesting that we can do if we use what's called previsit and postvisit orderings. And so in this, we make another modification to depth first search. We initialize a counter, which we call clock, at the start of DFS. And then we modify explore as follows. So the new things in explore are right here. Oops, maybe lines 2 and 3 and line 8. So when explore gets called on a vertex and we set visited to true, we define a variable for that vertex as this clock. So for the first vertex that gets explored gets stamped with a pre-value of 1. Then we increment the clock and do this loop over edges. And then when finally, this is going to be a recursive call, right? And this will explore some other vertices. Each time a new vertex gets explored inside this recursive call or inside explore GV, clock will get incremented. Finally, we emerge from all these edges. And at that point, we mark the end time that this vertex V was processed with post V. So it's the new value of clock, right? Clock got updated inside this for loop, and then we increment clock again. So it basically pre-marks when did we first start processing vertex V. It then goes down, through searching the neighbors of V and its neighbors and its neighbors. It finally emerges back up. And at that point, it marks the post of V with the time it finishes processing that vertex. So this is also a new line. So these lines 2, 3, and 7, 8 were added. So pre records the time that explore is first called on V. Post records the time that this call finishes. And then for a vertex, we can define the time interval, which is kind of like what's the time that I was processing that vertex or its descendants, the ones I found from it. And it's just the interval starting at time pre-V and ending at the time post-V. Okay. So let me give you an example of what this is doing. So I'll draw a graph. Okay, and let's say that, in depth first search, when it's looping over vertices, so let's go back for a second here, it always loops through them in order, like from 1 to 6 in this case. So the first vertex that's going to get processed is 1, then 2, and so on. So in our call to DFS, we begin at 1. We mark it with a pre-value of 1, and then it goes and it explores its neighbors. It begins by exploring 2. 2 then gets marked with a value of 2. That's its pre-number. We then go and explore to 4, right? This gets marked with a pre-number of 3. There's no other neighbors of 4, so its explore call ends, and the time gets incremented, or the clock gets incremented once more, then goes up to 2, which the time closes with 5. It goes up to 1, vertex 1, but it has another neighbor, so it now explores down here. This was the last time of the clock, right? So it gets incremented once more with 6. Then that gets closed with 7. And then it comes back up to here and closes it with 8. Now in DFS, we go back, check for vertices we haven't found yet. It will then process 5. It opens, the pre-time for 5 is going to be 9. Then it goes to 6, 10, 11, and then ends with 12. Right? Finds this. And so these are the pre and post times for each vertex. So this is the pre time for vertex 1, and this is the post time for vertex 1. And you can see what happens, right? Since vertex 2 was explored within the call to 1, this interval from 2 to 5 is contained inside this longer time interval, right? Like let's say this time interval, it starts at time 1 and it ends at 8. Here it starts at time 2 and it ends at 5, right? So this time is contained inside this. And you can see all of the ones you found from the initial explore on 1 call are contained inside 1, 8. You got 2, 5, that's inside 3, 4, 6, 7, and so on. And then these ones are disjoint, right? Because they were called in a separate explore call. But 6 is the interval for 6 is contained in the interval for time. This time interval from 10 to 11 seconds is inside the 9 to 12. And so this is a general property of these pre and post numbers, is if we take any two vertices, U and V, and their corresponding intervals, then they satisfy one of the 3 conditions. Either the time intervals are disjoint, like 1, 8 and 9, 12, right? They don't share a common time. You have that U is contained in V, or you have that V is contained in U, right? So like an example of this is that I2 is contained in I1, because the interval 2, 5 is in 1, 8. And similarly, I4 is contained in I2. So the proof of this is kind of follows almost directly, but let me just make the argument here. So we have that pre of V marks the start of explore GV, and post V marks the end. So for a vertex U, either 1, you just have the 3 options. 1 is explore GU is called within explore GV, which would imply that IU is contained in IV. 2 is the reverse. Explore GV is called within explore GU, in which case you have that IV is contained in IU, or 3, that they were separate connected components. U and V are in separate connected components. And then you have that IU and IV are disjoint. And those are the three options. Now, before I give an example, I just want to, or like another example of this, I just want to review some graph terminology. We've kind of already talked about a fair bit of this, but I think it's useful to just remind ourselves of these different terms, or if you haven't seen them before, tell you what they are. So a cycle in a graph is a path that starts and ends at the same vertex. An undirected graph is a tree if it is connected and it contains no cycles. So a tree could look like right? That's a single connected component and it has no cycles. An undirected graph is a forest if it contains no cycles, but it's not necessarily connected. So an example of this could be right? That's a forest, that's a tree, because that actually has two components. A rooted tree is a tree in which one vertex is designated the root. So the only difference between a tree and a rooted tree is, let's say I call that the root up there. Now it's a rooted tree. If I define the root of a tree, then that gives us a natural ordering of all the vertices given by the distance from the root. So for example, I could take, let me just draw one of my examples here. Like this, call this the root. Now, one thing I could do is I could assign a direction pointing away from the root for every edge, and then it's called a directed rooted tree. So for example, I could draw arrows like this, going away from the root. And now this is a directed rooted tree, or also called an out tree. And then once I have this root and I have this notion of like things going out from it, then I can talk about parents, child, ancestors, and descendants. So a parent of a vertex V is a vertex that's immediately above it on the tree, on the path back to the root. So for example, if I take this V, then this is a parent of, this is the parent of V, right? And you can see in a tree, it just has the one parent. And a child of a vertex is a vertex for which V is the parent. So this could be the child of V. And let's call this one U. And then an ancestor of a vertex V is any vertex on the path from V back to the root. So we could say the root is an ancestor of this vertex U. And a descendant of V is any vertex for which V is an ancestor. So for example, this vertex U is a descendant of R. So we have U is a descendant of R, and we have the R is an ancestor of U. Right, so parents are just one hop. I mean, it's just really like a family tree, the notions of descendant and ancestor. Okay. So now with this, I can give an example, and this example will be helpful to illustrate some further properties of these pre and post orderings. So I'm going to draw a special, like a graph that I kind of constructed that illustrates all the things I want, which is, so it looks like this. It's a directed graph. 1, 2, 3, 4, 5. And it has the following edges. So it's got edges going out here. down to 4, down to 3. All right, so I've got, sorry, this one I want to point the other way. So I've got edges going out 2 and 5 and 3, then an edge from 4 up to 1, edges going into 4 from 3 and 5, and an edge going in from 3. Okay, so now let's run DFS on this. And again, we'll start at the lowest numbered vertex. So the pre and post orderings are going to look like this. So we open here with 1. From 1, it calls on 2. 2. Then it finds 3 from there, has a pre-time of 3. 4. From the vertex 4, there's no unvisited neighbors, right? The only outgoing neighbor is 1, which has already been visited. So we close this with 5. We close this with 6 because there's no other neighbors for 3. Close this with 7. And we come back up to here, but 1 still has another neighbor, which is 5. So then we go out here. We open that with 8. It has no unvisited neighbors, so it gets stamped with 9. And then we come back up to here and stamp this one with 10. Okay, so when DFS is run on a graph G, it creates a collection of directed rooted trees, which we call the DFS forest. In this case, right, in this example, this is the root up here, and then it's just one directed rooted tree with these kind of 2 branches. Each edge in the DFS forest is, if an edge is in the DFS forest, then like the end point of the edge was found while exploring the tail, right? So 4 was found while calling explore on 3. 5 was found while calling explore on 1, right? While exploring the neighbors of 1, and so on. And so there's several different kinds of edges on this graph. The first one is tree edges. So a tree edge is an edge that's in the forest, and the interval for the head is contained in the interval for the tail. So all the blue edges here are tree edges. Let me just label one of them. So this is a tree edge. Also, this is a tree edge, this is a tree edge, and this is a tree edge. A forward edge has the same thing, that the interval for the head of the edge is contained in the interval for the tail, but it's not in the forest. So do you see an example of that, where one interval is contained in the other, but it's not a blue edge? Yeah, so one example is this edge right here, right? Because the time interval 3 to 6 is contained in the interval from 1 to 10, but this is not a blue edge. So this is a forward edge. Forward edge. Another kind of edge is a back edge. So UV is a back edge. If the tail of the edge, the interval for the tail is contained in the interval for the head. This can't be in the DFS forest. So let's try and find an example of that. So where's a case where the edge points to like a bigger interval, a superset, right? Well, right here, this is a back edge. And so you can see, right, this interval 4, 5 is contained in the interval 1 to 10. And in this case, in the case where we found a back edge, then V, the head of the edge, is an ancestor of U. You can see that's true, right? The root here is an ancestor of 4, or in other words, 4 is a descendant of the ancestor. And then the last kind of edge is a cross edge. And a cross edge is an edge where the intervals IU and IV are disjoint. This edge is also not in the forest. And so a cross edge is right here, right? 8, 9 is disjoint with 4, 5. Those two time intervals, if we lay them out on the timeline, do not have any overlap. So this is a cross edge. And the thing that you'll notice in this is that if I follow these tree edges, followed by a back edge, it makes a cycle. Because the back edge points back up to an ancestor. And by definition, if 1 is an ancestor of 4, then there had to be a path from 1 to 4. And so this is actually a way that we can detect cycles in directed graphs. So recall, a cycle is just a closed path in the graph. Like we go around on vertices and we come back to where we started. And we say if a graph has no cycles, then we say it's acyclic. So one example of a graph with no cycles is a directed rooted tree. So let me just draw another graph. With some directed edges. Right, this graph contains a cycle, which is right here. So this is not an acyclic graph. And the way we can find out if a graph contains a cycle, a directed graph contains a cycle, is as follows. A directed graph, a directed graph has a cycle if and only if the depth first search reveals a back edge. So that's exactly like what I was drawing here, right? This is a cycle. We take the tree edges followed by a back edge, and that gives us a cycle. So let me now try and convince you of that. I think you kind of see it in the picture, but let's prove that property. Notice that it's an if and only if. That means if a directed graph has a cycle, then the DFS will reveal a back edge. And the reverse is true. If the DFS reveals a back edge, then the graph has a cycle. So this is kind of, when we draw this kind of implication, we write it like the arrow pointing both ways like that. And so then I really, in proving this property, I have to prove both directions. So let's start by proving the direction going this way. This one's actually kind of easy. So we prove that if DFS reveals a back edge, then we've found the graph has a cycle. So, and the argument is really just going to be exactly what I said above about the ancestor thing. So let UV be the back edge. By definition, U is a descendant of V on the DFS tree. So there's a path from V to U. If I just take this path from V to U, followed by the edge UV, I've found a cycle. So therefore, path V, draw it as kind of like a squiggly edge to U, V to U, followed by UV is the cycle. And that's exactly what I was showing here, right? The path from 1 to 4, followed by the back edge from 4 to 1 is a cycle in this graph. So that proves the one direction. To show the other direction, I'm going to kind of show it. You can read in the notes, it gives the full explanation, but I'm just going to draw it, illustrate it essentially. And I think it makes the point kind of clear. So let's suppose now, when we're showing this direction, we're saying the directed graph has a cycle, and we want to show that then DFS reveals a back edge. So the graph has a cycle. Let me just draw that cycle. So this is, so the graph, oops. And so let's say that's the cycle. It has some vertices on it. Let's call it V1, V2, V3, V4, V5, and so on, right? I mean, it doesn't necessarily have 5, but whatever. And so some vertex on this cycle is the first one that DFS finds. So let VI be first vertex on cycle found by DFS. So for example, I don't know, let's say it's V3 here. All other vertices on the cycle are descendants of V3, right? Since they haven't been found yet, and they're connected to V3. So they'll all get found. Now I call explore on V3. All of these ones are still marked to false because this was our assumption, as V3 was the first one to get found. And so they'll all be found in the explore call from V3. Right, so when we do this explore call, we'll then find this one, this one, this one, and this one. And then if you look at this edge right here, going from V2, the last one on the cycle before V3, back to V3, this is the back edge. So therefore, the edge VI minus 1 to VI is a back edge. Right? And so that means, though, then that we have a nice way to check if a graph is acyclic or not. So we can determine if a directed graph is acyclic by running depth first search and checking for a back edge. So how do we do that? Here's a quick algorithm to do that. Checking if G contains a cycle. Run depth first search with the pre and post numbers. Then do one loop through all of the edges. And so for each edge, UV, we check if IU is contained in IV. If this triggers true for some edge, then we found a cycle. Otherwise, the graph is acyclic. So IU contained in IV just means that pre-U has to be greater than pre-V, and post-U has to be less than post-V. Right? So the IU starts later and it ends earlier than for V. And if you look at the runtime of this first part we know is big O V plus E. And then the second part is just a loop over the edges. This is big O of E. And so the overall runtime is big O V plus E. So why are we interested in directed acyclic graphs? They show something about causal relationships. So they might show that a task U has to be performed before a task V. And then if you have a cycle in a graph, it doesn't make sense because you're saying, I have to perform, let's say 1 before 2, I have to perform 2 before 3, and I have to perform 3 before 1. There's no way to do that, right? It's a cycle. So in acyclic graphs, it can show a workflow of a set of tasks. And that means that there should be some way to order the tasks that satisfies all these calls. Okay, so this leads us to the idea of topologically sorting a graph. A topological ordering of a graph is an ordering of the vertices such that for each edge, UV, U comes before V in the ordering. If there's a cycle in the graph, then this isn't possible, right? So like one example, like just to give you, is it's sort of like you lay all the vertices out on a line, and then all the edges go to the right in the line. So they could go something like this. And there's lots of different ways I can arrange these edges or these vertices on the line. And a topological ordering is an arrangement such that all the edges go from left to right. And so the question is, if the graph is if the graph has a cycle, there's no way to do this. There'll always be an edge pointing backward on this line, no matter how I order the vertices. But if the graph is directed in acyclic, then every edge leads to a vertex with a lower post number. And this property gives us an algorithm for topologically sorting a graph. So let me just first show you, go back to one of our examples. So it says every edge leads to a vertex with a lower post number. So here it's 10, it leads to 9. Here it's 10, it leads to 7. 7 leads to 6. 6 leads to 5, right? Because in every case in this edge, explore was called at the end point of the edge before it was called at the start point. So the start point finishes after, right? And that's the property that gets exploited. And so basically, if we ran depth first search, got the post numbers, and then sorted them in so that the lowest post number comes last, that would be a topological ordering. And so the way to do this without having to actually sort them is as follows. Run DFS to compute the finish times post for each vertex. As a vertex is finished, at each time it's finished, insert it onto the front of the list of a list. And then that list is a topological ordering. So insert it onto the front of the list and then return the list. So the vertex with the highest post number comes first because the last one to finish gets inserted on the front of the list, and the lowest post number comes last. So we are sorting in reverse order of post number, but we're able to do this in still big O V plus E time. Right? An alternative would just be run DFS and then sort by post number, but then you're going to get, it's going to run in big O V plus E for depth first search, and then you have to do a sort, which is going to be V log V. And so that won't always be better than this, right? So this is a way to ensure that we get it in V plus E time. So let me give you like a kind of silly example of topological sort. And it's inspired by the cold weather outside. So let's say that we want to get dressed for the winter. And we have several things that we've got to put on. We have, we have a hat. We have gloves. We have a sweater. We have a jacket. We have snow pants. And we have boots. Okay, and I'm going to draw some causal relationships between these. I think that the hat should go on before the gloves because it's hard to put your hat on with gloves. Similarly, you should put your jacket on before you put on your gloves. You definitely should put your sweater on before you put on your jacket. Maybe you've got those snow pants with the suspenders, and so you kind of need to put that on before you put your jacket on. And then I think your boots have to go on, after your snow pants. And also you got to put your boots on before you put your gloves on, because otherwise it's really hard to do up your laces. So this is, let's say, our graph. We run depth first search with the pre and post numbers. Let's say it starts at hat. So it, or actually, sorry, let's say it starts at sweater right in the beginning. So it matches what we did in the notes. So this gets opened. It then searches the neighbors. The only neighbor is jacket, so it gets a 2. Then the only neighbor of jacket is gloves, which gets a 3. Gloves has no neighbors, so it closes with 4. Jacket closes with 5, and sweater closes with 6. Now we have to call again. Let's say it calls over here. Depth first search continues, right? It goes 7. It explores down to boots, which gives us an 8. The only neighbor of boots is gloves, which has already been visited. So this gets closed with 9 and then 10. And then finally, hat still has to be explored. So then it gets called with 11 and then it gets closed with 12. So now we sort in reverse order of post number, right? So that means the thing that goes on first is the one with the highest post number. So this has a post number of 12. This has a post number of 10. This has a post number of 9. 6. Jacket is 5. And gloves goes last. And so the order that we get, the topological ordering of this graph is hat, pants, boots, sweater, jacket, gloves. There you go. That's how you get dressed for winter. So the thing you can see, right, is actually this isn't unique. There's several solutions. For example, had our depth first search started with hat instead of sweater, we would have got something different. You'd still get some of the same like things occurring, right? Like sweater always occurs before jacket, and sweater and jacket and boots and pants will all occur before gloves always. But similarly, I could have started. This is also, a valid start point. Any of them are for a depth first search. And so each one you would get a different potentially slightly different ordering that still satisfies all the causal relationships. And if you were to just redraw the graph with the vertices in this order, so we put hat here, then we put pants and so on, all the edges are going to go from left to right when you do that. So that's topological sorting. Very briefly, I'm just going to mention connectivity in directed graphs because it's a little bit more subtle. We're not really going to go into it at all, but there's multiple notions of connectivity when we get to directed graphs. The two common ones, but there are others as well. One is called strongly connected. And so a graph is strongly connected if for every pair of vertices, U and V, there's a directed path, so I can obey the arrows on the edges, and I can get from U to V, and I can also get from V to U. This is quite a strong notion of connectivity, right? Because there has to be paths in both ways. Another notion is called weakly connected. And so a graph is weakly connected if it's connected when I just delete the arrows on all of the edges. So just the underlying kind of undirected graph is connected. So, this graph here is not strongly connected because there's no path from this vertex back to here, but it is weakly connected because if I delete all the edges or all the arrows, there's a way to get from any vertex to any other vertex. So anyway, there's some interesting things about connectivity with directed graphs. We won't go into it more here, but that's the end of this lecture, and I'll see you in the next one. All right, bye everyone.